We're ultimately interested in Goodstein's theorem. In the language of arithmetic, the way we set it up, Goodstein's theorem is, for every x, there is a y such that gy of x equals 0. Remember, gy of x is the function which tells us what the value of the Goodstein sequence starting with x is after y steps. So this says that for every number x, there is some big enough y. So if we look at the Goodstein sequence starting with x, after y steps, we've reached 0. We showed that z infinity deduces all true facts about the natural numbers, so in particular that z infinity deduces Goodstein's theorem. Our proof was explicit. It told us how to construct that deduction. Goodstein's theorem is a for-all sentence, so we should use for-all introduction. So for each natural number n, we should have a branch where we deduce there is a y such that gy of n equals 0, and there are infinitely many of these branches. How do we deduce these? Well, we happen to know that there is such a y. That's what we proved in the previous part. It wasn't an easy proof, but it's done. So we can deduce there exists such a y using the exists introduction rule. We know that there's a natural number m, so that gm of n equals 0 is a true atomic sentence. So if we just choose the right m in each branch, we get the deduction we want. This is not an interesting deduction. In particular, it's not telling us anything useful because the key step, all the work, is in choosing the right m, and we only know that the right m exists because of all that work we did earlier. None of the interesting information, nothing about how we find m or why we know it exists, survived into this formal deduction. That is not how a deduction system should work. Deduction systems are supposed to be a restricted kind of proof. They're supposed to account for how we know things. So we're going to add a requirement. It makes our system more complicated, but it will rule out what's wrong with this deduction. Most deduction systems fix this problem by restricting the for-all introduction rule, or whatever the equivalent is. If you've seen a more typical finite deduction system, that's probably what it did. They don't say you get infinitely many branches and you can do something different in each one. They usually say, if you want to prove for all x phi, the way you prove phi of x is replaced by n has to follow some kind of rule. There has to be some kind of pattern to the branches. You can't just have a totally different proof for each n. That is not the approach we'll take. We're going to place the blame on the exists introduction rule. We're going to say that the problem is in the step where we deduce exists a y gy of n equals 0 from gm of n equals 0, and we're just sort of guessing at what m is. We only know it exists because we did this big complicated proof, and in particular, m is really big. We're going to restrict the exists introduction rule. We're going to say that when we deduce there exists an x phi from phi of x maps to n, we don't want n to be too big. And then we have to decide what too big is, because of course there's no objective standard about which numbers are too big. It's not like n should be less than 10 billion. If phi is the statement, there's a number larger than 10 billion, deducing that from 10 billion and 1 is larger than 10 billion seems pretty reasonable. So here's what we're going to do. We're going to define bounded deductions. When we have a bounded deduction, we're basically saying we have a deduction and it's not too big. Our measurement of the size of a deduction will have two parts, an ordinal and a natural number. So we'll write this with the bounds on top to mean there is a deduction of gamma, which is bounded by the ordinal alpha and the natural number k. And what we need to do is repeat our definition of the rules of z infinity with additional information about how these bounds work. We're always going to have the requirement that the complexity of alpha, tau of alpha, is less than k. With the true rule, that's the only restriction. We can deduce the true rule with any bounds that satisfy the requirement that tau of alpha is less than k. Consider the and introduction rule. When can we deduce gamma with phi and psi with the bounds alpha, comma k? To deduce gamma with phi and psi, we should have a deduction of gamma phi and a deduction of gamma psi. And to deduce phi and psi with bounds alpha k, the deductions of phi and psi should be smaller. They should have smaller bounds. And that should be reflected in the ordinal. So the deduction of phi should have bounds beta k, and the deduction of psi should have bounds gamma k, where beta and gamma are ordinals that are less than alpha, and they should continue to have complexity less than k. This pattern, that the premises, the previous deductions, should have bounds which are smaller ordinals and not much more complicated, repeats in the other rules. In fact, for most of the rules, that's all we have to say. For or introduction, weakening, contraction, and cut, in order to use these rules with bounds alpha k, we need to know that the previous steps had bounds beta k, where beta is less than alpha, and tau of beta is less than k. The for all introduction rule has a small additional twist. Remember, to deduce gamma with for all x phi, we're supposed to have, for every n, a deduction of gamma with phi of x replaced by n. If our deduction of for all x phi has bounds alpha k, then for each n there should be an ordinal beta n, which is less than alpha and not too complicated, so that z infinity deduces gamma with phi where x is replaced by n. But the complexity is going to depend not just on k, but also on n. The bound on tau of beta n should be the larger of k and n. And along with that, the numeric bound on the deduction of gamma comma phi with x maps to n should also be the larger of k and n. A for all introduction rule has infinitely many premises. They all need to be shorter, but the complexity can depend on n as well as on k. So to deduce phi of 10 billion, we're allowed to use a more complicated ordinal than to deduce phi of 1. Finally, the exists introduction rule is the only rule where we change the rule itself. When we deduce exists in x phi, we require that the witness be bounded by h alpha of k, where h alpha is the alphth function in the fast-growing hierarchy. That's a complete description of our rules for bounded deductions. There are a bunch of different schemes for describing bounds on deductions, and the choice I made here is a little unusual, and that choice comes with some trade-offs. This approach is mixing together two ideas. The ordinal is measuring the height of the deduction. You can think of a deduction as a well-founded, infinitely branching tree. We have statements justified by other statements, justified by yet more statements, and we put these all together into this big branching tree, and it's well-founded. If you follow any branch long enough, you eventually reach a leaf, one of the axioms. And the ordinal part of the bound is telling us about the height of this tree. If I start at the bottom, at the conclusion, and follow a branch back towards an axiom, every time I go from a conclusion to a premise, my ordinal counts down. And by the time I reach 0, I must have reached an axiom. That's the main point of this ordinal part of the bound. It's telling us how big, how tall our deductions can be. But we're mixing that height measurement with a measurement of complexity that is telling us how big the witnesses to exist statements are. That's what this natural number k in the bound is doing. The main point is in the exists introduction rule. The number k, helped by the ordinal, is telling us that the numbers we need to demonstrate that this exists statement is true won't be arbitrarily big. We actually have some information. We have a bound on how big that n is going to be. Or to put that another way, in a regular deduction, an unbounded deduction, when we have an exists introduction step, the number n, the witness, seems to vanish. But when we have a bound on the deduction, we're keeping some information about n, at least about the size of n, around, because we're remembering what alpha and k are, and knowing alpha and k tells us how big the witness n is allowed to be. The complication is that if we're not careful, if we're sloppy in the way we define ordinal bounds, it turns out that we can misuse the ordinal bounds in a way that will cause us to forget that information. That's why we need this restriction on tau of beta. The advantage to mixing these parts together is that we need both of them, the height bound on the deduction and the complexity bound on the witnesses, to get the result we want. And it is a lot less complicated to do them both at once, rather than having to do almost twice as much work to deal with one part and then the other. The disadvantage is that mixing them together makes it a little harder to see how both pieces work, because they do interact a little. So as we go forward and we talk about bounded deductions, we'll keep looking back at these two separate aspects. We'll keep saying, when are we talking about how big the deduction is, and when are we talking about how big the witnesses are?